Are we ready? Hi, everybody. Welcome back to school. Creepy Screen is back. I'm back. So I have a question for you. How many of you woke up this morning or yesterday and felt like this? Hang on. Wait for it. Wait for it. Hang on here. We gotta get the audio. Can you hear it? No. Okay. Gotta get the audio. So this is my son throwing a fit this morning.
Sweetheart, Mommy has to go to work today. Mommy,
This is how one expresses displeasure.
go to work today. I'm sorry, buddy. It's time for you to go back to school, and it's time for Mommy to go back to work. We're not going back to school and work.
We're not. Anyone else wake up that way today? Now he's 2, so he gets a pass. But the good news is that an hour later, he was successfully at daycare and was so excited to see his friends again that he didn't even notice I left. So the hardest part is always waking up, right? Adding a new section to your to-do list. But we're here, we're ready. And in case you're wondering what he looks like when he's not throwing a fit, this is his school picture. This is Huey. So, doesn't happen all that often, but he occasionally is not throwing fits. So anyway, hi. For those of you who haven't met me before, and there's a couple of you, I'm Lesa. I will be your instructor this semester. Don't call me Dr. Hoffman. The only one who calls me that is my dad because he thinks it's funny. Just call me Lesa, and that's fine. Hopefully everybody got the email I sent out yesterday. Yes? Okay, I didn't get any bounce back, so I think that's good news. This is CLDP 945 Advanced Multi-Level Models. We will be in this room from 1:15 to 2:30 on Mondays and Wednesdays. I hold office hours in this room after class from 2:30 to 4. The idea is that you get to use the office hours as a group-based lab time to work on assignments, to talk to me about the assignments or anything else that you want to work on. If you'd rather make an individual appointment to talk to me, that's fine too. I just like to be able to have a group-based office hours. That way, if you get stuck on something, I can help you. You can move on, and I can move on to someone else's questions. Let's see. So we have our web page. I have a printable syllabus, but that I will never bother to update. Everything in terms of the schedule, the most current version is going to be on this website, so please check that for materials. Since we're in a lab, I don't feel the need to print anything, but if you're old school and you like working with paper, please plan on bringing some for yourself. The homework system is not yet available because we've had some late ads, and so I want to make sure that I get everybody's IDs, and so we'll talk more about that next week. That will be available. All of the homework this semester will be online. We'll talk about that later. Readings are in Blackboard. Were you able to find those course documents? Okay. In terms of software, this class, like the previous semester, is going to use SAS predominantly. I have arranged to have everyone have remote desktop access to this room. Within Blackboard, there's a list of IP addresses, and each of you has one targeted with your name that you can use to log into this room whenever it's not in session. I also posted the course schedule for this room so that you know when that is. SAS University Edition hopefully is still working. Most of you, it seemed like, got that to work reasonably well. If we don't run out of time and we actually do make it through all of the stuff on the syllabus, the last section I will be teaching you the same type of models within M+ software, which is also available in this room. I don't plan to have any homeworks using M+ though, so you don't have to worry about having personal access to it. That's because it's really expensive, and I don't want you guys to have to pay for anything that you don't need. Let's see. What else? Oh, a few things that are different. I'm doing differently this semester relative to previous semesters. Your participation in this class is going to be based on homework assignments, which is most of the points, as well as quizzes. But based on the feedback I got last semester, we used to do them in class. It used to be just participation based, and people felt like sometimes that was helpful, but not always, because they weren't always prepared. Sometimes you get behind, and I understand that. So this year I'm trying something different, which is to have them due before you come to class. So you can work on them at home. It'll be the same format as before, just a couple short answer questions. You get points for completing it. So making an honest effort at completing it. Since you're at home or wherever you're working on this, you can look up the answers as needed. But the idea is for you to ask yourself, how much do I remember off the top of my head, and to use that as a guide to help you know what to review or what to prepare. As well as if you don't know the answers and you can't find them, then we'll go over it in class. So I have on the syllabus, subject to change based on how well we go through things in terms of the timeline, when these quizzes are due. I have set them up to be every other week. So once a week you'll have a homework due. On the off week you'll have a quiz due. So one thing every week, hopefully. And we'll get a chance to go over them in class once as a means of reviewing content. So that will be, we'll see how that goes. Readings, I have some of the chapters from my book that we started last semester, and I have a whole bunch of other readings. I'm not super excited that you complete all the readings, I'll be honest with you. I've given you readings as more of a resource for when you want to go back and look at these models in greater detail later, as well as if you need to be able to cite something in a paper. So these are more sort of FYI types of readings, except for the ones in my book, of course, because I wrote it. I spent 5 years writing that book, and you will read it, right? It's in English, right? There's words and everything, and pictures, stuff like that, right? Right? So let me see from my memory how many of you I remember, because I got some new faces here. This is Lucas with a K. This is a new face. What's your name?
Yeonju Kim.
Yeonju?
Kim.
Yeah. What do you go by?
Yeonju.
Yeonju. Okay, try and pronounce people's names. Jihan, is that right? Sarah, Aaron, Heather, Scott, new person. Are you Jacinta? Okay, you don't have a picture on the thing, so I had to guess. Well, everyone else has a photo roster, so you haven't been to get your KUID yet, I bet. Yesterday, okay, it hasn't made it in the system yet. But we have Teresa looking all dressed up today. No, it looks like a jacket. Okay, sorry. Yeah, I'm wearing hiking boots because the last time I was in the parking lot where there was this much ice and dress shoes, I bit it. So I was like, no, it's not happening. Heather and Brittany, you have a picture, so I know who you are. Damn it. Claire. I know. See, here's the thing. I know about your red, green, and like up, down, and the data we talked about, and I don't remember your name. This is the problem. Yes, the set of you are sort of like lumped together in my head, even though I know each of you. I'm sorry. Andrew, welcome back. You have a baby now, right? Is he yelling at you yet, or she?
She does yell.
Okay, good.
She's 8 months, so she's still in kind of the like cry yell.
Cry yell.
But shifting from cry to
Okay.
which I think is developmentally appropriate.
It is. And next, by the way, after cry yell is this. That was anger for a long time, and now it's with this like throwing gesture. And just in case that wasn't clear enough, it's no with an angry sound after. So I'll let you know what's after that as soon as we get there. Ejin. Okay, another new person. Kahi. Okay, so you're my late adder. All right, got you. Amy knows her. And Katie Jo is back. Is your baby yelling at you yet? Yes. Cry yell. Does anyone else have babies that are yelling at them? Anyone? No? Well, you don't know what you're missing, let me tell you. I'm glad that daycare has started again. I thought daycare was going to start on Monday, and I didn't realize that he didn't have daycare on Monday. And then yesterday morning, my husband woke me up and said, I have bad news. There's no school today. Whenever LPS is closed, daycare is closed. And I was like, oh, not again. More yelling, but we're here and it's okay. So in case you're wondering why I'm wearing this lovely punch of metallic, I record all my classes, not the video, but what you'll see is what's on the screen here as well as my audio, and they will be available on YouTube. So I'm going to set up a YouTube channel for this class. That way, if you are unable to attend class, you can watch via YouTube. And if you want to hear whatever I have to say again, you can watch via YouTube. So I will put the links to the videos next to the links to the material as I have been doing for several years now. So that's me. That's you guys. Any questions before we jump into things? I'm back to water today because I've already had my quota of caffeine, if you couldn't tell. No one wants to talk. We're all good? So let me guess, you remember everything perfectly and you're ready for new material. That was a joke. Thank you for laughing. No. So I put together a little review for this class. I don't know if we'll get through it all today. We might. It has some new slides in it, and it has some things that are rearranged differently because I found that when I was thinking about how to review, the order in which I presented it is not necessarily the order in which I want to review it. So it'll be the same stuff, but just a little bit of a twist. And also per your feedback from last semester, as a means of reviewing, I have 2 sessions planned of what I'm calling story time, where I have a list of real data sets and real people that I've worked with, and I want to go through the process of thinking about, given a set of data, a sampling design, and a set of research questions, what do you do first? What do you do next? How do you think about it? So that you'll be able, hopefully, with more practice in your lives, be able to recognize types of problems and the types of models that go with them. So the content of this class is really, it's building on just your basic sort of 2-level model. In order to learn multi-level models, you have to have at least one context to draw from. It's really hard to keep constructs in your head as just level 2 or level 1 when they don't mean anything. So that's why we started with just time within person. But the rest of the gig here is building on that with more types of complexity, more types of sampling designs, not just longitudinal, but also people nested in groups, or what's called clustered. So by the end of the semester, you will have a really facile set of tools to be able to analyze all different kinds of data. That's the goal here. So away we go. Starting on slide 1 of lecture 1, reviewing concepts. So, what are you learning? These models go by all kinds of different names, and I want you to know them so that when people ask, oh, is this a blah, 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 you can say, yes, it is, or no, it's not. I like the term multi-level. I think that's the most useful because it's descriptive. Other people will call these models general or generalized, as we'll talk about in a second, linear mixed models. That's more of a statty type of term. Random coefficients models is another term that gets applied to these models. And I'm highlighting here that anything that involves latent variables or factors, latent variables are random effects. So we're hedging into what people call structural equation models as well. Hierarchical linear models is a term that gets used more often in the School of Ed, so HLM as the acronym for that. But broadly construed, what all of these things here have in common is that they are designed for samples that have dependency. Dependency sounds like a bad word, right? Like if you're codependent, that's bad, right? Dependency is an assumption that's broken and we got to solve it. Dependency just means correlation. It's the idea that sampling observations from the same something are more related than observations from a different something. Occasions from a person, people from groups, people from families, that sort of thing. So under that general umbrella, you get all these particular instances of this general type of model. So repeated measures ANOVA or random effects ANOVA is where we started with last semester, and I'll review that briefly. That's a special case of this, when you just have a particular type of variance model. Growth curve models, that's what longitudinal models are often called if the focus is on change, systematic individual differences in change. Daily diary, ecological momentary assessment, Palm Pilot-y, how old am I? Let me guess, smartphone-y? What's the acronym now? There's one that Chris Cushing uses all the time, and I can't remember what it is off the top of my head. I'm bad with names, even for inanimate objects. But like all of these like collect data and give you immediate feedback kinds of studies, these models work very well for those kinds of studies. If you're studying kids, whether or not you care about their classrooms, teachers, schools, districts, and so forth, the model has to care. So these models work well for those situations. Cross models, cross-classified, cross-random effects, anytime you have multiple dimensions of sampling that are not nested, they're crossed. And also everything you know under the heading of measurement models. Confirmatory factor models, item response theory models, item factor models, diagnostic classification models, all of those types of models are items nested in persons. So it's all the same thing. So this is a very versatile tool that hopefully you will have more knowledge of by the end of the semester. So my focus here, I'm trying to give you a framework on which to hang more detailed pieces of information. And the way that I view these models is by conceptualizing the two sides of them, and then we have different procedures and different rationales for each side. So model for the means, model for the variance. These big picture terms. Model for the means synonyms include fixed effects, the part you're used to caring about. When you think about a model, you think about what's my outcome, what are my predictors, do they have main effects, do they have interactions, are their effects linear or nonlinear, all of those kinds of decisions about how a predictor relates to one or more outcomes. That gives you the structure of the model for the means. Structural model and other synonyms. That part you get started with in your very first sets of stats classes, and that part is a lot of that part is the same in these models that we're working on. The part that's different, the model for the variance. That's the part that is new and exciting because you have lots of choices to make that are based on both theory, design, and data. Stochastic is a word that goes with this, error terms. So error, residual, random, stochastic, variance. All of those terms go together in your head. This is the part that you're used to making assumptions about in the world of regular regression or ANOVA, and that's the part that we get to make lots and lots of choices. And so that's the model for the variance is really the big focus here. For example, here's what a regression model looks like for an outcome that is collected once per person. So just regular old cross-sectional data where you have a sample of individuals. Model for the means is highlighted in red. The idea that each person's predicted outcome is built from a common intercept and a common slope for each of these predictors. In this case, I have X, Z, and their interaction. So this model has 4 parameters, 4 estimated things, 4 fixed effects within the model for the means. For those of you who were with me last semester, what does fixed mean? Start off easy. Everybody gets the same. And if I look at this equation, how do I know that those betas are fixed? That everybody gets the same beta. What don't they have on them? The I. They don't have a subscript for a person-specific version. Everybody's predicted outcome is built from the same beta 0 plus the same beta 1 plus the same beta 2 plus the same beta 3. Each person gets their own X and Z, but if somebody has the same value on X and Z as somebody else, they get the same predicted outcome. So the fixed effects work together to create a conditional mean, a predicted mean. The other part here, the other side of the model for the variance. If I only have one observation for an outcome for a person, all I need is one kind of variance. E is what's left. E is all of the difference in the outcome among people who have the same X and Z values. And in a regression model, we don't estimate each separate E, we estimate its variance. We call that thing residual variance, leftover variance. And in a regression model, they tell you that E has to have 3 characteristics. They call these assumptions. Independence, E's are normally distributed and they have constant variance. Well, Those are all choices. Doesn't have to be that way. If you don't like it, change the model. So terminology then to describe what models have that allow you to violate these assumptions, meaning how do we change the model so that we don't assume those things anymore? We can assume dependence, we can assume some other kind of distribution, and we can assume non-constant variance of particular patterns. So first distinction, general versus generalized. Ized means not normal. So the residuals can have some other kind of distribution, such as for binary outcomes, categorical, ordinal, nominal outcomes. Those things are called multinomial, as sort of a big picture term. Count data, zero inflated data. There's all kinds of other distributions besides normal out there. So if you have an outcome whose residuals are never going to be normal, you pick something else. No biggie. The term linear, by the way, shows up in all of these. That refers to the idea that these models are linear in their parameters, not necessarily linear in their variables. So what linear in your parameters means is that your predicted outcome is composed of something that goes intercept plus slope times variable, plus slope times variable, plus slope times variable. It's a linear equation that gives you a predicted outcome. Slope times variable could refer to a quadratic effect, or a log of the variable, or some other nonlinear form, but it gets multiplied in a linear fashion. A truly nonlinear model would have like an e in it or something like that, e to the. So if you're moving from this general linear models world to generalized, one of the first changes you have to make is letting go of the idea of least squares. Least squares is what you're taught as an undergrad, how you calculate f-tests and mean squares and all that stuff. That's only possible if you're in general linear models. Once you leave that family, we work with something called maximum likelihood, or perhaps Bayesian estimation instead, which is similar to maximum likelihood but has extra stuff involved. But the thing that unites these two models is that they are both designed for data that are independent. One observation for an outcome per sampling unit. If that's not the case, then you have the same setup of some kind of normal versus ized not normal whenever you have multiple dimensions of sampling. Whenever you have some kind of dependency, where each person has multiple outcomes or multiple occasions or multiple items. In that case, we pick up the term mixed in the middle. Mixed means that we have both fixed effects and random effects. Fixed means everybody gets the same, random means everybody gets their own. And this semester, I have plans to do both of these things. So, ized is harder than non-ized, only in the sense that you may not have seen it before. But if you've done logistic regression, if you've done like account regression or something like that, you can do the multi-level model version of it just fine. So we will get there a little bit later on. Okay. Questions? So if you're asking the Google, what kind of model do I need? These are the types of terms that you would ask about, right? These are the things you want to look up in the STATA manual or the SAS manual. Practically speaking, though, the kinds of designs that require these last two general linear or ized linear mixed models are these kinds of things. So longitudinal data, we're going to cover this semester in more complexity. So we started with just two-level occasions within persons. We're going to pick up complexity in the form of how occasions are sampled. For instance, the first topic that we'll do after reviewing is what's known as an accelerated longitudinal design, as well as multiple levels of time. So accelerated longitudinal designs, I'm trying to remember, now I've lost your name. Man in the back with the baby who yells at him. Andrew, see, I remember your data. I have no idea what your name is. But you have the data from a small school district nearby where you have like third graders, fourth graders, fifth graders, right? And you follow each of those cohorts over time. That's an accelerated longitudinal design. And what makes that more complicated than the two-level models we've been looking at is that time is both between persons and within persons. We have 3rd, 4th, 5th, 6th graders at the outset, and we have how they change over time. So at a minimum, you have grade, and then you have time. And how do you set up the model to account for both of those things? There's several different ways to do it, some of which are easier to understand than others, some of which are wrong, quite frankly. But we'll talk about that first off as a way of reviewing longitudinal. We also have multiple levels of time on tap. So what are known as measurement burst designs, where you have something like multiple observations within a day across multiple days, or multiple observations, say, within a 2-week period that are repeated every 6 months. Those kinds of designs where you have 2 levels of time that require 3-level models, so there's additional complexity there. Multivariate models. Whenever you're trying to measure the same thing for multiple people, for instance, dyadic data or family data, whenever you want to know how one outcome relates to another. So does stress cause declines in cognition, or do declines in cognition cause stress? That kind of question. Those are answered via multivariate models. So we'll stop by all of those variations this semester, as well as questions about mediation, which I personally hate, but I know lots and lots of you need to know how to do it, so we're still going to do it. Repeated measures not involving time. So we'll stop by models for items crossed with persons, such as what not Heather is doing, right? How's that? What Claire is trying to learn, where she's trying to stick a cumulative logit model in there. We're going to do that. We're going to do sampling designs in which the same people respond to the same items. And how do you analyze that? Even though it's not longitudinal, it's repeated measures. It might happen within one testing session. And then last but not least, clustered and cross-classified data, where you have kids within classrooms, within schools, within districts, that kind of thing, or people sampled longitudinally within groups where they change classrooms every year, that kind of stuff. So we'll get all of that done too. So all of this falls under the heading of general linear mixed models, ISed if the outcomes that we're talking about are some kind of not normal. How are we doing? Are you excited? Yeah? No one wants to talk to me. It's okay. You can smile and nod. That's good enough. So, bigger picture thing here. How do we deal with dependency? All of these sampling designs, what they have in common is one or more kinds of dependency, one or more kinds of correlation. So if I have just occasions within a person, that's one kind. Person causes dependency. But if I have, say, occasions within days within persons, that's at least 2 kinds. Occasions from the same day may be more related. Days from the same person may be more related. So each of these has one or more kinds of dependency. How do you build a model that predicts it, that addresses it? One is as a fixed effect. So this is a common solution in econometrics and in certain other areas where you treat the dependency as something to get rid of. It's not something to explore, it's something to be solved. So for instance, if I'm doing a longitudinal study and I don't have enough people in my current location and I need to borrow people from, say, 2 or 3 other sites. People from the same site more likely to be similar to each other than people from different sites. But I don't care about site. I just got multiple sites so that I can get enough people. That's a case where I would put in which site is which as a fixed effect, as a predictor, and that controls for site differences. If I put it in as a main effect, that controls for intercept differences specifically. If I want to control for the fact that people in certain sites might improve faster than other sites, that would be site multiplied by time. So if you have dependency that has relatively few units and you don't care why it's there, fixed effects are your game. We will rarely do that in this case because it doesn't allow prediction of why those differences occurred. Second is to build some kind of multivariate variance-covariance structure. That's a mouthful. But what I mean is you have some kind of observations within a person just think about the correlation matrix across those, where you have, say, the variance of time 1, 2, 3. Let me get a picture here. So variance of the first outcome, the variance of the second outcome, the variance of the third. On the off diagonal are the covariances, 2, 1, 3, 1, cove 3, 2. This just says, well, okay, I have 3 observations per person. I'm just gonna let them be correlated. The end, right? They are, so what? And how you pattern this thing gives you such choices that we talked about last semester, such as VC. Anyone remember what that stands for? Variance components. That says there's no correlation here. That says no covariance whatsoever, equal variances. That's one choice. The H in parentheses for each of these stands for heterogeneous, meaning let the variances be different instead of the same. CS is another choice. Remember that one? Compound symmetry that says, okay, there is covariance, but it's all the same. Doesn't matter which occasion it is, which outcome it is, all the same. AR1, autoregressive. The covariance decays as a function of how far apart in time, where 1 unit in time is correlated R, 2 units is R squared, 3 units is R cubed, and so forth. And TOPE, what does that thing stand for? Topelets. I always want to put an extra E in there, topelets, but it's topelets. And that's another one based on lag. You know, yes. Because you will never find me in autoregressive pants ever again. These are topelets pants. These are somewhere between straight or boot cut. Yes, thank you for that. Yes, and unstructured. What kind of pants are unstructured? Athleisure, sweatpants, yoga pants. I did think about that today. I was like, you know, those yoga pants that I've been wearing for 3 weeks, I really don't want to part with them. But no, I put on real pants just for you guys. I washed my hair and everything. Yes, and compound symmetry, do you remember what kind of pants those were? Skinny jeans, yes. Skinny jeans are okay for some cases, but not for everybody, myself included. So if we're talking about these set of choices, we're not talking about levels. We're talking about a single level data structure with multiple outcomes, where the outcomes get to have some pattern of relationship. That's another way to deal with dependency. The last one is the one that's the more complicated, the one that is more flexible, which is when I say add a level. When I take multivariate data and I'm talking about it using a multi-level terminology, what I'm talking about is adding random effects, random intercepts, and random slopes. So that's the thing that I want to spend the most time on here, because these are also creating patterns of non-constant variance and covariance over time, but they do so for more kinds of data, because it can be non-constant variance and covariance not just over time, but over any kind of clustered or nested observation. So adding a level. For instance, adding a level to talk about longitudinal data. Rather than talking about longitudinal data as just having some kind of correlation pattern, let's talk about it using levels. Level 2, people. Level 1, occasions. So here's your synonym list here. Level 2 is inter-individual differences. Level 1 is intra. Level 2 is between. Level 1 is within. And when I say people, level 2 can actually be anything that's measured repeatedly. So I think, Lucas, you had something maybe with countries measured repeatedly? Yes, right? So you have the people nested within an occasion within a country. You've got 3-level data, but like your people are countries, right? Or they're not countries, they're like religious groups. See, I know your name is Lucas. I am winning today. Yes. Okay, well, let's do that one, yeah. So, let's see. I'm trying to think of who else I've spoken to who has something other than people. Anybody else? A lot of you deal with people, right? It's a people-centered kind of lifespan institute place over here. But yeah. So you'll just have to do the mental gymnastics when I say people, think of whatever it is that's sampled repeatedly. So other things that you have to think about in characterizing longitudinal data. And then we'll get into these nuances this semester. What should time be? Well, time is time. What do you mean? Well, it's not always that simple. So Andrew, still winning. For your study, the small children in a place nearby study, what's time?
Well, we have grade as a proxy, but then also
Semester,
classroom.
classroom.
We also consider
Age, because like a bunch of, let's say, first graders can be anywhere from what, maybe 5 to 7 with a mean of 6. So yeah, if you have that kind of data, it's not necessarily obvious what time should be. Another instance is when you're dealing with process. So if you wanted to track, say, changes in depression due to treatment, something like that. Well, what's time? How long you've been in this particular study? How long you've been in treatment of any kind? How old you are? Like, all of these things are different choices. So these are choices that one has to make whenever time has variation that is both within and between. So time thus far has been exclusively a within person variable, which is level, which is within? 1 or 2? 1, yes. So if time is between, it is also level 2, yes. So Andrew's example is a classic case where he has grade, because you have your 3rd graders going from 4th grade to 5th grade to 6th grade, but you also have your 6th graders going from 6 to 7 to 8. And the question to answer then is, okay, does it matter when you were in 6th grade? Are all 6th graders alike? Can you just draw one big trajectory and be like, this is what change looks like? Or does it matter which year you were in 6th grade? Well, if the school does anything different, it's going to matter which year you're in 6th grade, in addition to just all of the normative changes you would expect between grades. Anytime you have a study of adults that vary in age at the beginning, you have to worry about this. Anytime basically you have people who vary in the time metric you're interested in at the beginning, that's when you have to worry about this. I'm trying to think of examples. Let's see, the actual Heather. So you have the Fragile X study, right? How many, what is the age range of the children you studied at time 1, whenever they walked in the door? 11 months and 40 months. So do you think it's different if a child begins, that let's say that they're diagnosed with something at 11 months versus 40 months? Probably. By the time they get to 40, they may look different than if they just got diagnosed at 40, right? Hopefully, right? That's what the point of treatment is and all these sorts of things, right? So you have to worry about this. You also have to worry about it if you're tracking their moms, which I know you do, right? So if you're tracking changes in mothers of children of different ages, what's time going to be? Is it how old the mom is? How old the kid is? It's different, right? So these are the things to think about, time being between and within. And then the last one are words that you already know, but just to remind you what they mean, balanced or unbalanced. So balanced means everybody's on the same schedule. Not necessarily equal interval, though. So if I say you're going to come back at 1 month later, 3 months later, 6 months later, that's balanced, even though the distance between times is not the same. But what matters then in terms of the models is keeping track of those distances. So if I say time 1, time 2, time 3, this is, let's say, 1 month later, this is 3 months later, and this is 6 months later. We'll have a time 0 here at the top. Which column goes in my model? The left-hand side that just keeps track of 1, 2 versus 3, or the right-hand side that keeps track of which time it is? Does it matter? I think it matters. If I'm going to have a slope for someone's change over time, what's a slope? Like if I said the slope is 2, Lucas, what does that mean? That's the intercept, the slope.
So basically, if you're going from 1 to 2 to 3, you're going from 1 to 3 to 6, you have alpha 1.
Yeah. So if the slope is 2, for every unit time, more time, your y outcome goes up by 2. That don't make any sense over here. If you want to know what a unit is, this change would be 4, whereas this change would be 6, if the slope is 2. So, balanced, not necessarily equal interval. If you have unequal intervals, you have to make sure you build that into your time metric. Unbalanced means people have different possible times. And this is a consequence anytime you have a time metric that varies between persons. Why does balanced versus unbalanced matter? It dictates a couple of things. Number one, it dictates whether or not any of these multivariate structures that we talked about are possible for you. You go back to this one. This section right here, that's balanced data only. Everybody has to share a common correlation or covariance matrix in order for you to say what kind of structure it has. Otherwise, that whole family of options is off the table. This last set of options, adding a level, is back on the table for unbalanced data. The other thing that I will mention as an aside is that the idea of testing absolute fit, whether or not you have the right model, is only possible for balanced data, because the right model is letting everything be what it wants, an unstructured matrix with saturated means. So that's the other reason why these two things matter. This distinction is really only relevant for time. If you have clustered data, nobody would ask you this. Balanced might mean you have the same number of kids in each class, but it's not like being child 1 versus 2 versus 3 means anything, the way that time 1 versus 2 versus 3 means something. So this is really just longitudinal vocabulary right here. Questions on that? All right, moving on then. Other things to think about when choosing what family of models is going to be appropriate for you and what needs to go in them. Are you anticipating change or fluctuation? You can end up with something somewhere in the middle, but this is the endpoints of the continuum. If you're on the change side, what you think about in terms of building the model for the means with respect to time is describing the average pattern of change. Is it linear or nonlinear, continuous or discontinuous, and so forth? Fluctuation, even though you may have a graph that looks like this, time might still be relevant in ways you hadn't anticipated. So for instance, if people give you different answers the first time you ask them than each subsequent time, you have to pay attention to that, even if it's not something you have a hypothesis about. Any kind of day of the week effect or circadian rhythm or scheduling effect. For instance, I know very little about stress and cortisol, but what I do know is that cortisol peaks 30 minutes after you wake up, and it comes down from there. Whether or not you care about that, you have to build something into the model that accounts for that if you want to look at cortisol reactivity for any other reason. In the model for the variance then, change models tend to be focused on random effects of time. Which aspects of change show individual differences? Do people need their own intercepts and their own slopes? How many different random slopes do they need? In a fluctuation model, people tend to be worried just about the relationship across occasions and making sure that the covariance is predicted accurately. Fluctuation models, if you don't have balanced data, there are very few choices. But we will get to that later in the semester, a couple of examples of how to build in different patterns of covariance across different levels of data. Please. Within person.
Within person.
Yep. So if you don't have people, you can just think of it as within whatever. But the idea is that this is the level 1 part of the model and what you're trying to build to reflect it. All right. So here's a trick question for you. Is ANOVA good or bad? Anyone want to take a vote? Brittany, you're smiling at me. What do you think? You don't want to vote? You just want to smile? Yeah. Well, of course, the answer is, it depends. But this is going to be one of the things that people will ask you about. It's either going to be, well, why didn't you just do an ANOVA? Or how is this different than ANOVA? So I want you to know this. When people use repeated measures ANOVA for longitudinal data, sometimes it's okay. It's okay when you don't have missing data. Repeated measures ANOVA, when people use that phrase, most of the time they're talking about least squares estimation. You can have missing data if you run a repeated measures ANOVA model using some kind of maximum likelihood, though. So it's estimator versus model as making a distinction. Repeated measures ANOVA models do not allow time-varying predictors when estimated via least squares. They require balance time, because what ANOVA means is saturated means. You have as many differences between occasions as you have occasions, with one more for the intercept. So a saturated means model, for instance, if I have 4 occasions, is a 3-degree of freedom test for a mean effective time across the 3. So we have to have time in nice, neat, balanced bins for this to work. The differences then between kinds of ANOVAs reflect differences in the model for the variance. What do they do for dependency? So here are your choices. A between groups ANOVA, between persons as I might call it, that's a VC. That means all the variances are the same, no covariance across time. You would never do that for longitudinal data on purpose. The two that you might do, the univariate approach, that's compound symmetry. The multivariate approach, that's unstructured. Now those represent logical endpoints on a continuum of complexity. Compound symmetry says one variance, one covariance, no matter how many occasions there are. Unstructured is as many variances and covariances as possible. So unstructured is the best you're going to do. It's not possible if you don't have balanced data and if you have a lot of data. So we're going to look at models that are somewhere in between compound symmetry and unstructured in terms of their complexity that hopefully fit as well as unstructured. So I'm going to return to this point in one of my stories because I helped somebody try to publish what we called a multi-level model. In reality, all she had in it was a random intercept, and one of the reviewers was like, "You can't do multi-level modeling with only 12 people." Be like, can I do a repeated measures ANOVA with 12 people? Because that's what I did. All right. So back to pictures. Empty model. What does empty mean? No predictors. If I don't know anything else about a person, what's my best guess for their outcome? The mean. So if I have between person data, an empty model would look like this. If I move to longitudinal data, here's what it would look like if I had 5 occasions. All the error is between what's predicted and what's observed for a single person here. If I have 3 people, 5 occasions each, we take that same idea of if I don't know anything, I predict the mean, but we say, no, 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 I know from which person each occasion came from. So now I can predict a better mean, I can predict an individual mean. And this is the jumping off point for being able to model dependency, being able to predict some kind of covariance across occasions from the same person. So in this picture, I have 2 kinds of variance depicted. I have the person's mean and via the dotted line here for my people of 3 different colors. Why doesn't everybody have the same mean? Why do people differ from each other? Ugh. That's called level 2 random intercept variance. It's the variance across people in this new term called U0 for intercept specifically. After factoring in that people need different means, I say, why are you off your mean today? Why are you more or less than you normally are on a given occasion? That's E, that's what's left. That's level 1, and that's residual. In notation, use tau squared for any kind of random effect variance, sigma squared for level 1 residual. So it looks like this when you put it together. If I have my purple person here, they have dependency in the sense that they are always below the grand mean, the black line. So I account for that dependency by giving them a U0 that says, okay, I'm going to shift their whole predicted trajectory down constantly over time. And after factoring that U0 in, what's left should look like our normal assumptions in regression. Normally distributed, independent, constant variance. That's the idea. So by splitting this outcome into two kinds of variance, I have induced a correlation. U0 is responsible for the correlation between occasions from the same person. That's it. This is univariate repeated measures ANOVA. So pairing the empty models side by side here using the single level notation, U0 is the difference. U0 is always phrased as mean zero. So if I am above everyone else all the time on average, my U0 is positive. If I am below everyone else all the time, my U0 is negative. In multi-level modeling terms, this simple version here looks like that. So this is the simplest two-level model that we would ever entertain. In this context, we're sticking with the idea of longitudinal. So I have level 1 here, YTI, the occasion, the outcome, at each time for each person, is a function of beta 0 I. That thing is not a parameter. That is a placeholder. It is a placeholder for how each person gets their own intercept, which is then an outcome at level 2. So level 2 describes all the ways that people differ from each other. Right now, it's an intercept, and that's it. So that Y-looking thing here, remember what letter that is? Gamma, yeah. It looks like Y in this font. It looks more like a V in other fonts, but I'm using it to be consistent with the notation that's in the book, which is similar to other people's notation. This is my fixed intercept. This is the mean of the person means. U0 then is how far off my mean is from that grand mean. So it's a deviation. So the estimated parameters, this is my fixed effect here, my fixed intercept, is U0 an estimated parameter? No. The model doesn't give me a U0 per person. It gives me what instead? Feel free to read from the screen. There. Give me a V. Variance, yes, not a trick. I warn you when I'm going to trick you. Yes, U0 variance. Just like we have E variance, residual variance, we have U0 variance. So this is the simplest model, starts with 3 parameters. You put them back together again without the placeholder, it looks like that. From that model, we get a very useful piece of descriptive information, intraclass correlation. In a 2-level model, there's only one possible. In more levels, there's more than one possible. ICC, it is the average correlation across occasions from the same person. It is also the proportion of total variance that is between persons due to the random intercept. It is the proportion of your outcome that is cross-sectional or longitudinal. Cross-sectional, yes. It's the part that's between persons. It's the part that would have been there had you measured everybody only once. ICC ranges from what to what, folks? 0 to 1. Which value means game over? 1. And I say game over because an ICC of 1 means you do not have longitudinal data. So you can analyze the between person part of the model just fine, but the longitudinal part is not going to go so well because it doesn't exist. Anything less than 1, play ball. We then talked about adding time into the model. 2 questions. Is there change on average? Are there individual differences in change? The first question is about a fixed effect related to time. Second question is about a random effect. So we have these pictures here. Top left, no fixed, no random. So if we tested a fixed effect of time and it was non-significant, and we tested a random effect of time and it was non-significant, that would indicate our data might look something like this. So I say no fixed because on average, the mean line, the heavy black line here in this picture, does not change across the x-axis, which is time. No change on average. No random because everybody, no changes the same. Next one. Yes, we have a fixed effect of time. On average, people are going up. However, no random effect because they're going up the same. These are the only 2 pictures on this slide for which a compound symmetry model would be appropriate. Remember what COP means? Variance model, compound symmetry? It means random intercept only. It means equal variance across time, parallel growth, and equal covariance across time as well. So if your data look like this, go ahead and run your univariate repeated measures ANOVA. You're fine. However, if your data look like either of these pictures, these are pictures of random time slopes. People need their own. Whatever happens on average does not describe the sample. And I include picture C here to highlight the fact that you don't have to have a significant effect of time as a fixed effect to go looking for a random effect of time. You can have either, neither, or both. They answer different questions. Fixed is there some kind of change on average? Random is, are there individual differences in that type of change? So if we put fixed linear time in the model by itself, so we go from picture A to picture B here, now level 2 has 2 new equations, one for beta 0, each person's intercept, and one for beta 1. However, beta 1 only has 1 term in it, the fixed slope. So everybody changes the same according to this model. That's shown a little more clearly down here, where we have just this common slope, no I subscript on it, multiplied by time. To add a random slope then, we pick up another term in the beta 1 equation at level 2, the U1. So it's U1 because it goes with beta 1. The subscripts, the first number is which beta at level 1 you're talking about. So in the equation for beta 0, they're all going to start with 0 because it's the equation for beta 0. Likewise, in the equation for beta 1, they're all going to start with 1 because it's beta 1. So these are structured similarly. Each individual term is some combination of fixed plus random. Fixed is what happens on average. Random then is how far off yours is from what happens on average. What also is joined in the model at this point, but is not listed explicitly on the slide, is that we allow a covariance between U0 and U1, because how you start is allowed to be related to how you change. Want to do this picture again? Remember this one? I like this one. You can hear me. So let's see what it would look like. The black line here is for the mean. The blue line is for one particular person from my sample. My x-axis is time, which starts with 0. Why does time start with 0 instead of 1? Whenever you change the scale of a predictor by adding or subtracting a constant, there's a word for that, right? There's a word for it. What's that word? Centering, yeah. So why did I center time such that the first occasion is 0? So my intercept is meaningful. My intercept is the expected outcome when all the predictors are 0. In that case, it becomes the expected outcome at the first occasion. If I had subtracted 3 instead, right, I could put the 0 out here, and then it would be -1, -2, -3. You can put it wherever you want. Within the data is a good idea, though. So here's my 0 point. That means my fixed intercept is my predicted outcome at time 0. It's what the model says it's going to be, not what it actually is. So it's the intercept of this line, not exactly where that dot is. U0 is how far off the blue person's intercept is. My blue person is starting out lower, so their U0 is negative. They get a U0 of -4, which gets them to their actual intercept of 6. The fixed slope, rise over run from algebra, change in y per change in x, to the best of my PowerPoint abilities, that's 6. My blue person, though, is growing more quickly, so their U1 is a +2 to get them to their slope of 8. And E then is the deviation between what the model says their line should be and what their actual data are. So for this person, their E is -1 here. It would be about +1 here, 0 here, and maybe -1 here. So this picture then depicts 3 different kinds of variance. U0 variance. Why do some people start out higher than others? U1 variance. Why do some people change faster than others? And then E variance. Why are you off your line today? Why isn't that line good enough? Why are you lower or higher than predicted? Are you with me? Good. So that's what it looks like here when we build these sequentially. Now drilling more vocabulary here. Remember my letters? G, R, and Z, and Z. Maybe. Maybe. So what I just said, 3 kinds of variance. They're going to show up on your SAS output or any other program output with these letters here. So you're going to get a G matrix. G is level 2. G is random intercept and slope variances. So each spot in G gets to be whatever it wants. So G is type equals unstructured forever and ever, amen. There's never a point in which putting a structure on this makes any kind of sense. The intercept variance gets to be what it wants, the slope variance gets to be what it wants, the covariance gets to be what it wants. Cool? Level 2, between persons, reasons why people differ from each other. Level 1 then is R. That's my residual variance. Now this particular structure is VC. Could I have it be something else? And feel free to read from the slide while answering. Sure. I could say, you know what? I think people need their own intercepts and slopes, but I also think that occasions that are next to each other are still going to be a little bit related. I could implement that idea by making this R matrix AR1 or Topolitz with only a lag1 correlation, for instance. And I could test whether the model fits better with that concession. So that type equals VC matrix is not set in stone. That's an assumption that you can then test. If I take G and R and put it back together again, what letter do I get? V. Yes, welcome to the jungle, folks. For those of you who are like, no, you can't put those together because those matrices are different sizes. I know, it's okay. We wrap G around another thing called Z, which holds the individual intercept and time values for each person. So we build each person their own custom V matrix using whatever occasions they have at whatever times they have. And that's how we handle missing data and unbalanced data. We build a custom V for each person. That custom V comes at a price, though. Because each person gets a different version of it using their own occasions, there's no way to test absolute fit. So all we can do is compare relative fit across models. All right. So these pictures, these models right here. This is linear time, right? Right? This is very simple from the perspective of saying that time has a very specific constant shape. What do I do if that is not reasonable? What do I do instead? Could I like add some stuff to make it look, I don't know, bendy? Yeah? How do I make it bendy? That's an easy way. I could take time squared. And if I add time squared, I create a bendy line of some shape. I can have a fixed quadratic, which means everybody shares a bendy, the common bendy. And I can have a random quadratic too, right? Individual differences in bendy. Do you remember the rule for what we do with quadratics? The magical number 2. Remember? You're like, no. Yes. Twice the quadratic is how the linear slope changes per unit time. So whatever your quadratic coefficient is, multiply it by 2 to talk about what happens to the linear as time goes on. And only one of 4 things can happen to it, right? Remember the 4 things? More positive, less positive, more negative, or less negative. The end. You just have to figure out which of those 4 quadrants you're in. So that's one kind of bendy. What if I had a study where I measured some people and then I like did something to them and then I wanted to see if the thing I did worked? Piecewise. So intervention phasey kinds of studies. Those would be, okay, I'm going to take one linear slope before and I'm going to have another linear slope after, and then I can compare the 2. Could I make each of those linear slopes bendy if I felt like it? Sure, as long as I had more than 2 occasions. By the way, how many is the minimum occasions to pull off this model? How many occasions per person do you need to fit this random linear time model? It's 3. What happens if I only had 2 occasions per person? I can't do a random linear time slope and an E. I can't distinguish what is individual differences in change from residual error. So either if I have 2 occasions, I either have perfect slopes or I have a random intercept with a residual. It's the same thing. So 3 is the bare minimum here. And as a follow-up question, some of you are thinking, well, what if some people in my sample have 3 but not everybody? Go ahead and try it. It may not go well. That will be my answer most of the time. Go ahead and try, and we'll see if it works. All right. So what we haven't gotten to yet is this idea of effect size and significance for things that go into each side of the model. But what I want to point out here is that what goes in with respect to time is dictated by the design, the type of data you have, and the questions. So you will see this always presented as the first example in any multi-level modeling or longitudinal modeling book. But sometimes it's the last example and it shouldn't be. So we will talk next time about stories in which linear is not the way to go. In fact, it doesn't make any kind of sense to start with linear. But the reason that we start here is because this is the easiest type of change to understand. It's constant. The most important thing to remember out of this is that each variable that's measured at level 1, so in this case we're talking time level variables, so this can be time itself, or it can be anything that's measured repeatedly, like stress or mood or health or anything like that. Each level 1 variable has the capacity to have a fixed effect and a random effect both. Either, neither, or both. Fixed means that's what everybody gets on average. Random means everybody gets their own of it. When you add a random effect, are you explaining variance? Do you remember? What are you doing? If you're not explaining variance, what are you doing? Making a new pile, and that's why the website for the book is pilesofvariance.com. We start out with, once upon a time there was an E, right? First thing we do is split E into 2 piles. How much is between, how much is within? Part of the within could be extra kinds of between. So part of the reason when we had this fixed linear time model in the middle here, part of the reason for E is that the same line doesn't fit everybody. We need different slopes for different folks. So what we used to think of as within-person error is actually something systematic to the person. It's another kind of dependency. So even though person is the only reason for dependency, it manifests itself in this model in at least 2 ways. Person differences in intercept, person differences in linear change. But you can do the exact same thing for any variable that changes over time. So if I have something like stress and health, are some people more affected by stress than others? Well, it's an empirical question, but what do you think? Any clinical people in the house willing to wager in? Are some people more affected by stress than others? Yes. Okay, you heard it here first. Does stress affect health? That's an interesting question, right? Yes, probably. Is stress bad for you? That's... let's call it the bad kind. Is bad stress bad for you? Not like the good kind, like I'm getting married or I have a marathon tomorrow, or like the good stress, like bad kind. Like my tire is flat, I'm late for work, and my 2-year-old is screaming at me. That's bad for you. Okay, on average, bad for you. How bad? That's the fixed effect. But are some people more resilient than others? That's the random. Next logical question then, what makes some people more resilient than others? What we're then talking about is expanding this level 2 model to add people level characteristics. Why are some people in worse health than others? Why are some people more resilient to stress? So each of these little pockets of dependency is something to be explained by other person level characteristics. Now, what complicates this and why we haven't talked about time varying predictors yet is even to answer that question, is stress related to health? There's at least 2 ways that you can think about that going in real data. People who are more stressed out than other people might be sicker than other people. That's between persons. That's what you would find in a cross-sectional study. But when you are more stressed out than usual, do you feel crappier than usual? That's within persons. So to properly talk about the effect of stress on health, I have to differentiate the piles of variance in stress the same way I would differentiate the outcome piles of variance in health. So I have to build a model that has multiple y's and multiple sets of betas at the same time, and that's multivariate. So even though these same concepts of fixed and random logically apply to any level 1 variable, any time varying variable, how it gets implemented is tricky because of the multiple piles of variance it contains. In this example, time is only level 1. It's only within persons, and that's why this is as straightforward as it is. Okay? All right. Then I shall see you next week. I will have something new up on the website before then, and hopefully, if you have any questions, you will talk to me now or otherwise. So, thank you for coming.